Glycolysis is the first step in the breakdown of sugar into energy, a universal process that is found in almost all living organisms. The goal of this process is to make ATP, which is the equivalent of the energy currency in the cell used to fuel many reactions. Chances are you've seen this process mentioned multiple times in your introductory biology courses, and were overwhelmed by the number and complexity of the molecules in the pathway. This video will be a short introduction into the nomenclature of the molecules. Studying the etymology of the names will also help you memorize the pathway. Now let's delve right in. Let's start with a quick summary of glycolysis. It is made of 10 individual steps, each a reaction of its own. These 10 steps are categorized into 3 different sections: an energy investment category, a molecule splitting category, and an energy extraction category. In the first category, as the name implies, energy is invested into the molecule. This section is composed of the first 3 steps. 2 ATP molecules are invested into the glucose molecule. The second section involves the splitting of the glucose molecule into 2 separate molecules. This category is composed of the next 2 steps in glycolysis. The last category is composed of the remaining 5 steps. This is when energy is finally extracted from the molecules. In these steps, 4 molecules of ATP are made. The original glucose molecule at this point has turned into 2 products we will talk about later. Glucose is the first molecule in this pathway. The name glucose comes from the Greek word glykos, which means sweet, since the only characteristic known about glucose at the time was that it was sweet. The suffix "-os" has an actual scientific meaning though. It implies that the molecule is a sugar. Putting these 2 words together makes glucose. In the first step of glycolysis, a phosphate group is added to glucose to make it glucose 6-phosphate. The reason for this is to add a charged group to glucose so that glucose can't cross the membrane and diffuse out of the cell. Glucose is made of 6 carbon atoms, which are numbered to help name the molecule. Glucose and glucose 6-phosphate are identical, except that on the 6th carbon, a phosphate group is now attached instead of a hydrogen atom. After this, the glucose 6-phosphate is converted into fructose 6-phosphate. 2 molecules are isomers of each other and have the same chemical formula. The name fructose comes from the word fructus, which is Latin for fruit, since fructose is found in many fruits. The suffix "-os" is used in fructose since it is also a sugar. The last step of the energy investment phase is the production of fructose 1,6-bisphosphate. Just like the carbon atoms in glucose are numbered, the carbon atoms in fructose are as well. Fructose 1,6-bisphosphate has a phosphate group on the 1st and 6th carbon, which is why the 1 and 6 are in the name. The prefix bis indicates that there are 2 phosphate groups attached to this molecule. The next step is the division of fructose 1,6-bisphosphate into 2 different molecules. The first is G3P, or glyceraldehyde 3-phosphate. The structure is similar to glyceraldehyde, with the exception of a phosphate group. The phosphate group is on the 3rd carbon, which is why the name has a 3-phosphate in it. The word glyceraldehyde comes from combining glycerol and aldehyde, since glyceraldehyde can be made by changing one group on glycerol into an aldehyde. DHAP is the second molecule, and this is an abbreviation for dihydroxyacetone phosphate. This molecule has the same backbone as dihydroxyacetone, except for the phosphate group. Dihydroxyacetone has the same structure as acetone, except for 2 hydroxyl groups on both ends. The dihydroxy implies there are 2 hydroxyl groups attached to the acetone. After fructose 1,6-bisphosphate is split into DHAP and G3P, DHAP is converted into G3P, which continues down the glycolysis pathway. In the beginning of the energy extraction phase, G3P is converted into 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate's backbone is glycerate, which looks exactly like glyceraldehyde, except that it has an oxygen on the end instead of a hydrogen. It also has 2 phosphate groups attached, 1 on each terminal carbon. Since 1,3-bisphosphoglycerate has 3 carbons, the terminal ones are numbered 1 and 3. The bis denotes 2 groups, and the phospho denotes the phosphate groups. In the next step, 1,3-bisphosphoglycerate is converted into 3-phosphoglycerate. In this change, one phosphate group is removed and used to make ATP. Since the phosphate group on the 1' carbon is removed, there is only one phosphate group left, which is why the bis is removed. So now, the molecule is 3-phosphoglycerate. 3-phosphoglycerate is converted into 2-phosphoglycerate. The only difference between these two molecules is the position of the phosphate group, which is moved from the terminal carbon to the middle carbon. Hence, the number changed from 3 to 2. 2-phosphoglycerate is converted into phosphoenolpyruvate. Phosphoenolpyruvate comes from pyruvate. Enol denotes that it is in the enol state instead of the ketone state. Here, you see the differences between the two. The phospho indicates that there is a phosphate group attached to the structure. The final step of glycolysis is the conversion of phosphoenolpyruvate into pyruvate itself, which makes a molecule of ATP in the process. Pyruvate is the final product of glycolysis that can be used in many different pathways in the cell, including lactic acid fermentation and ethanol fermentation. I hope that you have seen there are many patterns when it comes to naming these molecules, which is the reason they are named the way they are, so that someone can deduce the structure using only the name without any ambiguity. You should try doing this with some of these molecules yourself. Thank you for watching.